Okay, for what we have in section 3.5 in this simulation, we have for problem number 1, we're looking at solving for x, whereupon the base 36 logarithm of x is equal to 1/2. And just some things to mention. Now, whatever we have in the attachment, okay, the attachment has to be a positive value. Okay, so you cannot have a base 36 logarithm of 0 or anything that is negative. So x must be positive. Also, regarding what we have for properties of logarithms, whenever we have identical exponential and logarithmic bases, if you have the base a logarithm of a to the x, that goes to x. And also, if you have a to the base a logarithm of x, again, you have another case of an identical exponential and logarithmic base, and that is also going to go to x. And this property we will use in creating the pathway to solving for x. So we have for the base 36 logarithm of x equal to 1/2. Okay, so the base a is going to be 36. And if I treat both sides of this equation as powers to which the base 36 is going to be raised okay, so I have 36 to the base 36 logarithm of x. Okay, that is going to go to x. Now for 36 to the 1/2, okay, 36 to the 1/2, that is going to be the square root of 36. And for what we have in the outcome, okay, we have for this answer, okay, now we're going to have the x is equal to 6, and we have upon checking, and the result is correct. For what we have in the case of number 2, now we're looking at solving for x, and this time we have an equation. Okay, so we have the base 5 logarithm. We have of the quantity of 3x minus 7 is equal to 1. And again, whatever we have for 3x minus 7, 3x minus 7 has to be positive for that statement. That binomial is the attachment for what we have in this logarithmic term. Now, we're going to free up the 3x minus 7 from the base 5 logarithm. And again, we're going to apply what we just used for number 1. So we're going to have applying the exponential base, which will match up with the logarithmic base, and we'll treat both sides as powers to which the exponential base 5 is going to be raised. So we have 5 to the base 5 logarithm of the quantity of 3x minus 7 is equal to 5 to the first. And left hand side, okay, you have 5 to the base 5 logarithm of the quantity of 3x minus 7. This will go to 3x minus 7. 5 to the first is equal to 5. And here we have a two-step linear equation. So upon adding 7 to both sides, and we're going to have that 3x is equal to 12. And we have with division by 3, we're going to have that x is equal to 4. And 3 times 4 is 12, minus 7 is 5. So the attachment is positive. And just entering what we have for x and checking out. And it is correct. Now, for what we have in problem number 3, okay, so we have in this case, all right, so we have 2 times the base 3 logarithm of the quantity of x plus 28 is equal to 6. Okay, and in this one, okay, if you notice, you have even number coefficients on both sides, and so what you can do is that we can divide the equation by 2. Okay, and just a little bit of a repeat. Now the attachment in the base 3 logarithm, okay, we have x plus 28, and whatever we have for x plus 28 must be greater than 0. So as we look at dividing by 2, we're going to have the base 3 logarithm of x plus 28 is equal to 3, and freeing up the x plus 28 Okay, so we have a logarithmic term with the base 3 logarithm. And I'm going to treat both sides as powers to which the exponential base 3 is raised. All right, so we're going to have, on the left-hand side, we're going to have x plus 28. And we have, to the right, we have 3 cubed, which will be 27. And we have x plus 28 is equal to 27. And from this, we're going to have that x is equal to -1. Now, so while we cannot have a negative attachment, okay, now here x is a negative value, but the attachment has not x, but x plus 28. And so -1 plus 28 is 27, and that is greater than 0. And just testing out what we have. And the result is correct. Now, for what we have in the case of number 4, now we're looking at, it says to solve for x and round your answer to the nearest hundredth. Okay, so I have 7 plus 3 times, okay, the natural logarithm of x is equal to 2. And now we have a logarithmic term with 3 times the natural logarithm of x. And if I move the 7 over to isolate the logarithmic term, so you have the natural logarithm of x is equal to -5. And looking at, as we divide by 3, so we're going to have that the natural logarithm of x is equal to -5/3. Okay. Now keep in mind, a natural logarithm, okay, is going to be a base e logarithm. And before I get too far ahead, whatever we have for x, we need the attachment to be a positive value. Now we have for the natural logarithm of x, again, that's the same as a base e logarithm of x. And we have is equal to -5/3. And if I free up x from the natural logarithmic attachment, so I'm going to have e to the base e logarithm of x is going to be equal to e raised to the -5/3 degree. And so in taking what we have in the calculator, okay, so we have, with e, we have e to the x, and this is going to be to the -5/3. Okay, and so we have to the nearest hundredth, this would be to the nearest 2 decimal places. So you got a 0.1888. So to the nearest 2 decimal places, we have x is equal to 0.19. Then we have upon checking, and the result is correct. Now, for what we have in the case of number 5, we have that the natural logarithm of x is equal to the natural logarithm of the quantity of x minus 1 plus the natural logarithm of 2. Okay. Now, in looking at solving for x, okay, so we got, so you have the natural logarithm of x is by itself, and we have the sum of logarithms where we have the natural logarithm of the quantity of x minus 1 plus the natural logarithm of 2, and I can, with the properties of logarithms, now if I take the sum of logarithms in the same base, I can make it as a single natural logarithmic term upon multiplying out the attachments. So we have x minus 1 and 2 to multiply out. So we have the natural logarithm of x is equal to the natural logarithm of what is going to be 2x minus 2. And let me mention for the attachments, okay, I want x to be positive, and I want x minus 1 to also be positive. Now, in taking what we have now, so we have the same logarithmic basis on both sides, and we had the same logarithmic basis, and we have individual terms, we can go ahead and set the attachments equal to each other. But we can also just free up our expressions by applying the exponential base e. Okay, so we're going to have in the makeup, each natural logarithm of x goes to x, e to the ln of 2x minus 2 quantity. This will go to 2x minus 2. And working out what we have x by itself, and we can have this to be joined with the subtraction of 2x. X minus 2x is negative x. Negative x is equal to negative 2. And we have that x is equal to 2. And again, we have 2 is greater than 0. 2 minus 1 is 1, also greater than 0. And if we apply to what we have in the set and checking, and the result is correct. Now, for what we have in the case of number 6, okay, here we have an exponential equation that will share a common base. And here we have 8 to the x minus 3 is equal to 16. And here we're going to have a common base with the number 2. So you have, in this case, right, so you have a common base with 2. And for 8 to the x minus 3, now 8 is going to be 2 cubed. We have raised to the x minus 3 degree. 16, we're going to have it 2 to the 4th. For what I have on the left, applying the power property of exponents. We're going to have left-hand side, so for 2 to the 3rd quantity to the x minus 3, okay, this will be 2 to the 3x minus 9, and we have is equal to 2 to the 4th. Now we have the same exponential base, and we can now set the powers equal to each other. So we have 3x minus 9 is equal to 14, and upon adding 9 to both sides, so we're going to have that 3x is equal to 13, and for the outcome in the case of x, okay, we see we have x is equal to 13 over 3. And so applying what we have here, okay, so we have x at 13 thirds, and checking, and the result is correct. Now, for what we have in number 7, here we have e to the negative 8y is equal to 15. And it says to solve for y and to round your answer to the nearest hundredth. Okay, so we can get rid of the e if we take the base c logarithm of both sides. And again, a base c logarithm is going to be a natural logarithm. And here we have negative 8y is going to be base c logarithm of 15, which will be the natural logarithm of 15. And we have for y, we're going to have the natural logarithm of 15 divided by negative 8. Or you could say that we have y is equal to negative 1/8 of the natural logarithm of 15. Now we're looking at estimating and rounding to the nearest hundredth, which would be to the nearest 2 decimal places. And if we take, okay, what we have here, so if we have negative 1/8, okay, and just have the cursor blinking to the right, and so we have times the natural logarithm of 15, and so we have about a minus 0.34. And so just plugging in, okay, so we have, for y, have minus 0.34. And we have, upon checking the result, and we are correct. Now, in the case of the last problem, it says here, suppose that the number of bacteria in a certain population increases in accordance to a certain exponential growth model. A sample of 2,100 bacteria selected from this population reached the size of 2244 bacteria in 2.5 hours. And it says to find the hourly growth rate parameter. And it says that this is a continuous exponential growth model. Okay, and so for what we have, and it says to write write, to write your answer as a percentage. And it says do not round to any intermediate computations and round your percentage to the nearest hundredth. Okay, so we have just for what we have here, we have an exponential growth model. Kind of like for compound interest, you have future values equal to the present value times e to the r times t. Now, in this sample, we have 2,244 for the future value, and we say that the present value we have at 2,100, and we have e to the r times t. So we're looking at solving for r. Now for t, we're looking at 2.5 hours. And if I look at division by 2,100, so 2244 over 2,100 is equal to e to the 2.5r. And if I take the natural logarithm of both sides here, and simplifying the ratio is optional, again, we're getting rid of the e. So the right-hand side, okay, so we're going to have, to the right, we have 2.5r. You got the natural logarithm, 2244 over 2,100. And in the case of solving for r, we're going to divide by 2.5. So we'll just say we have 1 over 2.5, which would be 2/5. And we have times the natural logarithm of 2244 over 2,100. And just showing what this will look like on the calculator. So you have 1 divided by 2.5. So you have times the natural logarithm. So we have 2244 divided by 2,100. Okay, so I have 1 over 2.5 times the natural logarithm of 2244 over 2,100. And so you have for r, okay, you have 0.02652. And if I put this as a percentage, okay, so move over the decimal 2 places to the right, and here I have 2.652. And if I round to the nearest hundredth of a percent, so we're looking at 2.652%, and to the nearest hundredth, so you have right at 2.65%. So in terms of applying what we have now, okay, so for 2.65 for the percentage amount, and we have upon checking, and the final result is correct.